Okay, welcome back. We're on page 359 talking about the bin packing problem. Now, if the things coming off the conveyor belt are not sorted, or in the case of a grocery store, the guy doesn't bother to look at, oh, this is a jumbo box of Cheerios, it needs to go over here, and here's a box of matches, it's smaller, right? We're not necessarily talking about a physical sort. But if they're not categorized by size, the efficiency even goes worse. If they're not sorted and all you do is just take them blindly off the conveyor belt and put them in the sack without any thinking whatsoever about how big they are, then that's about 70% of getting it right. So you're off by somewhere between 50 to 70%. That is bad. I mean, really bad. So off by 50%, off by 70%. You can see how these things work. And clearly, if you had the time, the guy could say, well, wait a minute, hang on. If I put this one over here and put this one over here and move these things around, but obviously you don't have that kind of time. Okay, the next one we're going to talk about is the backpack approximation. It sounds kind of sort of like the bin packing, except in this case I have one or maybe two backpacks, and I'm getting ready to, bug out. And so I want to make sure I carry as much of the most valuable items that I own. So every item has a value and a size or maybe a weight or something. And so I want to put as many of the valuable things in, I put my jewelry and my gold bars and, whatever else you think is precious in a backpack. Okay? So that's the idea. The idea is to pick the most amount of things that'll fit. And of course, when the backpack gets filled up, you have to stop. Okay? All right. So here we go. Each item has a value and a weight or a size or something that would be the limiting factor. And you want to fill the backpack with the highest values, so total values, without going over that fixed size or weight kind of a guy. Okay. So you could sort by value first, okay? And then use the best fit technique, which is this guy right here. Okay? That would work. So what do you think? Is that going to cut it? No. That's back to 50% thing. So there's a thing called a subset sum approximation. That's a mouthful on page 361. And what they do is they sort by size or weight, whatever it is. And then you take the first pass. So the first pass, this is kind of a weird descriptor. So the first pass is I'll put some stuff in. And it looks like that the sum of, this first pass is, by the way, I don't know what my total weight is here. So this is kind of dumb. I guess it's 50. So these guys I can't do because they're over 50. And so then you take a second pass at them. And so you start flipping things around and switching things out, right? And so this first pass is, okay, I don't care what's in there. And then the second pass, you just pick things. And the next one, you say, okay, I'm going to go through and pick, these guys. And then you could go to a third pass or a fourth pass or a fifth pass. So this very much is the idea of the bagger going, look, after he puts the things in the sack, going, let me pull this one over here and put it over here and take this one out and put it over here. That is very much what this does. Okay? So the idea is this, so it found the optimal solution in 3 passes, which is not bad. Okay? It's coming up with the optimal solution. Okay. This next one is kind of a weird one. It's a math thing. Mathematicians talk about this a lot. And that is, if I have the map of the United States with the states all colored in. Let me see if I can find a decent one. So here is a map of states. So there's a mathematical theorem that says if you're building a map like this, that all you need is 4 colors, and that way no 2 states will ever be side by side using the same color. That's a mathematical theorem that says that that's the case. So I already know what the optimal solution is. The optimal solution is 4, okay? But we need to figure out how we're going to do this thing. Okay. So the idea is, getting close is about as hard as getting the optimal solution in these cases, because this is somewhat unique. In other words, getting the amount of effort to get you to 5 colors is almost the same as the amount of effort it would take to get to 4 colors. And so here the approximations really aren't helping you that much. They're not actually getting you anywhere. And so typically, if you just use this goofy technique that's in the book, the algorithm is on page 364, you're off by 100%. It's going to come up and say, it's going to take 8 colors to do this. It's like, wow. Really? So that first approximation just sucks. So this is, in mathematical terms, this is considered a planar. Okay, planar basically means, all on one surface. Okay, like no overlapping. So edges never cross. You're going to have 2 states where that claim the same spot of ground, right? They'll all just be edges matching perfectly. Cool. And so we know that, well, there's a mathematical theorem that says that this could be done in every case, in every map, done with 4 colors. Anyway, the algorithm sucks, is off by 100%, and the amount of time it takes to get to the approximation isn't that much better than getting to the optimal. It's kind of bad. Okay, so those are some very good examples of how these things work. So let's go back to backtracking for just a minute. So backtracking is a technique. It's not an algorithm. It's a technique. So navigating a maze, right? You guys know how to do this stuff. So here's a maze, and so I start off and I go here and I'm lost already. And then I have to make a decision right here. I go, wait. Do I go straight or do I turn to the right? So that I drop a marker, so to speak. I put something on the stack that says, hey, if I'm wrong, I need to be able to get back to this point. Okay? So just like dropping a pebble or something on the ground, you drop a pebble on the ground that says, I went straight. Okay? And then so if you go off in that direction and it doesn't work, you could come back to that point and go, last time I went straight, so this time I'm going to have to go this way. Okay. So here's how it works. You need to note the way you go, which way you went at every decision point. Every decision point you have to say, I came from this direction and I turned to the left. Actually, it'd be easier if it was like north, south, east, and west. That way, no matter which way you were facing, it would always come out right. But let's just make this common English. So this would be something you do like on a stack, because I could make a decision and make a decision and make a decision and make a decision and then go, wait, I need to get back 3 of these. Right? So perfect for the stack. Okay. There's another example of backtracking that kind of works the same way, and it's called the N queens problem. How many queens can you fit on a chessboard? Okay, remember how the queens work is the queen so I can't have anybody else in the horizontal, anyone else in the vertical, and anyone else on the diagonals. Okay? So a typical, 8x8 chessboard, how many queens can fit on this thing? And it's gonna be quite the same. It's gonna use that same technique. I'm gonna put it in a spot and then go check to see if I violated, and then I go, dang it. And so I'll go on to the next one and go, whoop, hang on, that didn't work. Let me just get back to where I was on the second one. Let's try someplace else, right? So it's going to be using the backtracking algorithm to solve the problem. So this is what's called the state space tree. It's kind of weird, but 4 items on the first row, 16 items on the second row, just kind of keep going with this little thing. And then there are 256 combinations of all this stuff, because, that's how many there are. And then all you have to decide is which one of these is promising and which ones are not. And if it's not promising, if it doesn't lead to a solution, you kick it out. Boom. That's how this thing works. So here's a highly generalized algorithm that basically talks in this is not really pseudocode. If there's a solution, then done. Otherwise, for every possible next step, do that thing that's kind of sort of promising, and then start over again. I know it's kind of simple, but obviously this is using recursion, which is a type of backtracking, kind of. that basically says try this, try this, try this, try this over and over again. Cool. Okay, I mentioned to talk about the branch and bound. Okay, so we're going to talk about that again on page 376. Remember, backtracking typically uses the stack in a tree, okay, a decision tree, right? I go down and I go, whoop, I could go to the left, I could go to the right, so it's a decision tree. And then stack allow me to back up and make a different decision. So branch and bound uses a queue, so it's the the breadth first approach, where I find all the solutions that are nearest to me and then move a little bit further away. So we'll create a bound number to determine if a node is promising or not. And then using the backpack problem, the node is not promising if the bound exceeds the total limit, right? In other words, I number all these guys and I go, well, that one's promising, that one's not, because I would blow my limit. Okay, so that's how this thing is done. And once again, there's a highly generalized that basically says throw this into the queue, and while the queue's not empty, is it better? Is this one better at whatever it is you're doing? If so, then go through and figure this out, and then put it back into the queue and keep going. And so it's the same problem. It's just instead of using recursion or the stack, we're using a queue. Okay, so you've got this, right? Which one uses a stack or recursion and which one uses the queue, right? Okay, good. I'm glad you're following along. Okay, the next one we're going to talk about is probabilistic algorithms. So this is basically one of those things where you guess, all right? Like if I make enough guesses, then most likely I'm going to come up with a really good answer. I'll explain why in a minute. So the example they give is an inscribed square, but that's kind of a dumb one. I'm gonna fire up a good old Microsoft Paint here, and we're gonna do one of our own. Okay, so here's Paint, and I'm just gonna go grab me a thing. And so if I said, what is the area of that curve? What's the area inside that curve? How in the world would you do that mathematically? I mean, I guess you could turn that into an equation, right? You could say, well, you know, this is x, y, this portion of the thing uses this equation, and that portion uses that, and that portion's... Oh my God, think about how much work that would be. Or you could cut this out and put it in a 12-inch by 12-inch piece of paper, okay? 12-inch by 12-inch piece of paper. Now, I know how much space is in a 12-inch by 12-inch piece of paper, right? Okay, that's 144 square inches, right? Okay, good. And I tape this to the wall, and I just throw darts at it. And all I have to do is count the number of darts that fall outside the line or inside the area. That's it. And if 50% of the darts were on the inside and 50% were on the outside, and it was 144 square inches total, then I would know that that would be half of that, right? Okay. All right? So in practice, what you do is you pick a random XY coordinate and just start plunking them down. Now, if you were interested in just a general idea how much area was being done by this, I guess you could stop at like 10, right? After 10 random numbers, you'd probably get a number. I'm not sure how good it would be. Maybe 100, maybe 1,000. See how you could just, the more time you spend on this, the better answer you're going to get. So I'm just randomly putting dots in here, and I'm just counting the dots that show up inside. And then I use that as a ratio of what I know the big size is, okay? Okay. So this is actually kind of cool. I'm just guessing and just throwing answers at it, and then I count up the number of guesses that worked and the number of guesses that didn't work. And then the ratio of the ones that did and the ones that didn't tells me what the correct answer is. Cool, huh? Okay, we're coming up on the 15-minute mark. You guys know how this works.